Hello, everyone. Let's go over this classic problem here involving implicit differentiation. So let's switch over to graph paper so I can, maybe small graph paper so I can fit this all in here. But what we have here is we begin with a circle, and the circle has radius 5. And we want to find the derivative dy dx. And so, of course, we all know about circles. And so why can't we find dy dx when we have the equation of a circle? Well, we can do that, but it's a little different from what we've done before with derivatives. So how's it different? Well, look, if I look at the entire circle, y is not expressed as a function of x. It does this does not pass the vertical line test. The circle does not. But still, we're not going to just say, okay, well, we don't like circles then. But of course, circles are sort of elementary, to say the least, in mathematics. So we should be able to work with circles. So one of the way we can look at this is that even though the circle doesn't pass the vertical line test, if we just look at a region of the circle, it does pass the vertical line test. So I'm just highlighting there. I'll probably erase that. But on that piece right there, the function passes the vertical line test. So if we restrict to that piece, we could think of y. We can think of y as a function of x. And when we find when we do find dy dx, remember one of the main applications or motivations for finding the derivative dy dx is the derivative is the slope of the tangent line. When we put in values for x and y, then we get the slope of the tangent line. So this whole problem could be about the question of, okay, what's the tangent line at a certain point, or what's the slope of the tangent line? And once we find out the slope of the tangent line, then we can find the tangent line. So the motivation for why we would find dy dx is to possibly we'd use that to find the slope of the tangent line, and then therefore the tangent line. So I've just drawn a circle. You don't really have to do that. But keep in mind we're assuming that y is a function of x. Okay, so what I'm going to do is just write down x squared plus y squared equals 25, and then we apply the derivative. All right, so I apply the derivative without solving for y. You could solve for y, but it would have a square root and you'd have plus or minus. This is, if nothing else, this is more direct to do it this way. Okay, so I apply the derivative both sides. Let's do the low-hanging fruit here, the easy part. Derivative of 25 is 0. And we go through and we take the derivative of each of these pieces as shown here. Okay, let me just write it this way. So I'm going to take the derivative of x squared. That's an easy one. I already took the derivative of 25 here. That was 0, so that was the easiest. And then I'm going to take the derivative of y squared, and I'm writing that in a certain way. But let me get to one thing at a time. So the derivative of 25 is 0. We already did that. The derivative of x squared with respect to x is 2x. Now, when I come over to y squared, I'm going to use the chain rule. This is going to involve the chain rule. This is we can think of this as a composition that's going on right here. There's a composition where I have y, which is a function of x. Like you could, y is a function of x. So you could even call this f of x. Whatever's inside there squared. Okay, when we use the chain rule, we sort of ignore what's inside there for a moment, and you could even call this, but this really gets confusing if I do a bit. You could call this u, and you take the derivative of u squared. That was the chain rule that we, that was the steps of the chain rule. But besides that, okay. So I take the derivative of this and I get 2. I ignore what's inside, if you want to call it u, whatever. 2, whatever is inside to the first power. But what's inside is y. And then, using the chain rule, I have to take the derivative of what's inside, and that's y. Y is inside. And so I multiply that, y prime. Now, when you do these problems with implicit differentiation, usually I don't think people are thinking through that every time. In practice, what you do is, look, we're taking the derivative, and we notice that we're taking the derivative with respect to x. The derivative of x squared is 2x. You could multiply by x prime. X prime is 1. But derivative of x squared is 2x. And then, see, this is the derivative with respect to x. When you get to y squared, you take that derivative, 2y, and then multiply by y prime. That's just every time you just throw in the y prime. Later on, in other applications, in another section, we'll take the derivative with respect to t, and then you would do, if the derivative is with respect to t, like time, like if x and y are functions of time, then you would write 2x, x prime, 2y, y prime. Maybe that was getting ahead, so let me just leave that aside. So now we'll solve for y prime. That actually ends up being the more difficult part. When we solve an equation, our unknown, as we are here, our known is y prime. What we do is we do actually the opposite order of the order of operations. So the last thing in the order of operation is addition, subtraction. And so when we solve, we do that first. And so what I'm going to do is subtract first and get 2y, y prime equals negative 2x. And then I'll divide y prime equals negative 2x over 2y. So y prime, or we can also call that sort of what we're supposed to here maybe, is dy dx. And dy dx is, as we see, is given in terms of both x and y. So if we are using dy dx here to find the slope of the tangent line, we need to find the slope of the tangent line at a point. So when we find that at a point, say we find that at the point 3, 4, for example, then what we would do is we would put in 3 and 4 for x, and x is 3 and y is 4, and that would give the slope of the tangent line. So actually, maybe I'll just go ahead and do that. So a follow-up, the slope of the tangent line at the point 3, 4 is dy dx equals negative. Okay, now what I'm going to do, I'm going to put in x equals 3, y equals 4. Those arrows are not meant to be anything but just look over there. They're not a limit or anything like that. Okay, so I should be careful about just willy-nilly writing arrows. And then the thing is about this dy dx, that's sort of not what I should do. Dy dx is negative x over y. So what you can do, but this is notation a lot of people don't really care for, is you could write dy, m for the slope is dy dx, and they write a line. Some people think this is a little bit overwhelming or sort of clumsy, but you could write at xy equals 3, 4. See, you can see why people don't want to do that. It's like too much. And then maybe someone who's watching the video will have a suggestion, you could write it more cleanly or more, a nicer, shorter way by doing something else, Oh no. But anyway, so but what I'm trying to express here is that once you put in the numbers 3 and 4, it's no longer dy dx. It's dy dx evaluated at at 3, 4. So the slope m equals negative 3/4. All right, so got a couple things there. I went beyond And not only did I find dy dx, which we got is negative x over y, we got the slope at the point 3,4 is negative 3/4, which is how this looks. We could probably use some other just trigonometry without calculus too, with some assumptions to find that slope of that tangent line. But okay, so this is on page 311 of the Openstax textbook, Calculus Volume 1. It's an open source book. You can look up on openstax.org and get this book free. And it actually has a work solution there too, if you want to look at that, see how they did it. But okay, so that ends the video.